How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is the enchanting phenomena associated with things that roll, rolling things, hoops and spheres and discs and the like. Consider the following. I have here a board which I can use as an inclined plane by raising it higher or making it lower, and here is a block of wood. We all know that if I raise the plane high enough, there comes an angle, there's a little stickiness there comes an angle at which the block slides. Indeed, if I had a block twice as heavy, we would find, if we explored it experimentally, that the block twice as heavy slides at the same angle as the one block alone. And I'm going to write the mathematics of that for you so you can have something to think about. It says, the mathematics says, that mg sine of theta is equal to mu mg cosine of theta. And from the algebra, you know, I can divide out the m, so the mass of the body does not matter when things slide. Now, when we consider things that roll, another interesting and enchanting detail arises. Here I have a disc of wood wherein we see the mass uniformly distributed. There is some everywhere with respect, say, to a central geometric axis. Here we have a hoop. The hoop has another property. All the mass of the hoop with respect to a central geometric axis is in the periphery, in the edge. So now, this brass hoop and this wooden disc have the same mass, but their distribution of mass is different. If then I put them at the top of the plane, since we see also they have the same diameter, the same radius, the same surface contact, which indeed doesn't matter a bit, we ask, how do they roll when I let them go? Do they roll together, that is, keeping neck and neck? Or does the disc win, or does the hoop win? And I'm going to show you how this does indeed come out. Watch it. And so we see the disc winning. Now I'm going to roll another disc. Here is a disc, aluminum, much smaller than the hoop, and I'm going to roll these together. This is a disc and still the hoop. And the disc again wins. Now I'm going to roll these two discs together. Small disc, big disc. It will be a little difficult to check this, but if our provisions for nature were of an adequate sort, I could show you the following phenomena. Watch it. Did we not, I must go further, did we not see this disc beat this hoop? Did we not see this disc beat this hoop? Let me take another hoop. Here is a hoop. Well, it's a long one with a long axis, but it's a hoop. And here is a disc. Watch now. This disc is beating this hoop. This disc is beating this hoop. Here is another hoop and another disc. This disc is beating this hoop. Let me take another hoop and a disc. This disc is beating this hoop. And what am I getting at? I'm getting at a most astonishing discovery. First, if I rolled all the discs in the world, I would find that all discs roll alike. Alike. I would find that all hoops roll alike. Little hoops, big hoops, fat hoops, skinny hoops, they all roll alike. Big discs, skinny discs, here is a disc, here is a disc, Now, because it has a long axis, we call it a cylinder, but I'm going to show you that that disc behaves the same with this hoop as other discs did. Watch it. And so I'm going to tell you another secret. All discs roll alike, all hoops roll alike. Now, all discs beat all hoops. All discs. So now somebody says, Professor, you have not lived long enough to roll all the discs and all the hoops in the world, so how do you know that? Indeed, no one has ever rolled all the discs and all the hoops in the world. But I have rolled discs and hoops in America, in Canada, in Africa, in Australia, and always I find that all the discs I roll alike, and all the hoops I rolled alike, and all the discs I rolled beat all the hoops. Now, I'm going to give you the argument, the proof that all discs roll alike. Here it is. I'm going to write some mathematics. FR equals I alpha. And somebody says, what does that say, Miller? I'll tell you what it says. It tells me that if I put the right stuff in there for the force and the radius and the mass distribution of the body called the moment of inertia, I get an expression for the angular change, the angular acceleration. Or I could write the potential energy at the top of the plane is equal to the kinetic energy of translation plus the kinetic energy of rotation. What I am getting at here, boys and girls and ladies and gentlemen, is this, that a proper understanding of the affairs of nature lies in the mathematics which describes it, because words are very weak. Now, I said that all discs roll alike and all hoops roll alike. The question now is, how about some spheres? Well, here is a big sphere, here is a middle-sized sphere, and here is a baby sphere. And if the board met my requirements and I let them all go at the same time, they would keep equal separation, and I would make a further announcement. The further announcement, all spheres roll alike. Now, the hoops that I spoke of have to be very proper hoops with all the mass in the periphery. The discs must be very proper discs, all the mass uniformly distributed, and the spheres must be very proper spheres, uniform mass distribution. The only question that remains now is this. If a disc beats a hoop, and all discs beat all hoops, and all spheres roll alike, how do spheres and discs and hoops roll? Well, we know this beats this, and so the question is, where does this come in the game? Well, look here. If I roll the sphere, excuse me, if I roll the sphere with the hoop, and something wins, watch it, I assure you that the sphere wins. You now know that spheres beat hoops, but what do spheres do with discs? Ho-ho! A wonderful thing. Watch it. We have a little trouble with this board, but that's another piece of evidence that when you deal with nature, spelled with a capital N, you must make such requirements as she demands. A little difficult to show it, the hazards of experiment, but I'm going to tell you. All spheres beat all discs. So if all spheres beat all discs, then all discs beat all hoops. If we let them go at the top of the track, the spheres always win, the discs come second, and the hoops last. Now I said that all discs roll alike. Here are two discs, and without revealing their nature, I'm going to roll them. Watch now. I'm going to roll them. Oh, one is winning, and yet they look like two uniform discs. No, they are not. So I have to reveal the secret. This disc, this one here, has some weights at the center. This one has the same weights on the edge. So you see, when the mass is farther from the geometric axis, the motion is slower. And I'm going to show you that. Here's the one with the weights lodged in the periphery, and here is the one with the weights lodged near the center. Watch now the motion. There it is. And so we uncover a most remarkable thing. And I would invite you, wherever you go in the world, find a disc and a sphere and a hoop and roll them and see if what I say is not true. Now concerning rolling bodies further. You all know what a yo-yo is. Here is a yo-yo. But before I go to that, I want to remind you, the only reason this body can roll, the only reason this body can roll is that there is friction between it and the inclined plane. Without friction, there can be no rolling. Consider the behavior of your automobile wheels on a very icy surface. They cannot roll. Accordingly, in the playing with a yo-yo, what do we find? What is a yo-yo? A yo-yo is a disc with a central axis around which is wound a string. So this is a body rolling on an inclined plane, which is usually vertical. Watch it. Oh, now do you see? There is not enough friction there for the gripping to climb back. Watch it, and I hope it doesn't work properly, because that will prove the point I wish to make. Oh, notice. Oh, there it is, there it is. It is not climbing back. If the friction is adequate, a very enchanting thing arises. Here is a yo-yo, a big one, with a small central shaft, and I'm going to let it go. And the point I wish to make here is this. When it gets to the bottom of its route, there is felt a sudden jerk, yank, pull impulsively in the string, and the thing changes direction and comes back up. How far can it come up? Never to the height from which it was released. Why? Because the energy of a system always goes toward less. Watch it. Well, we had a little trouble with the twisting of the string. One more business regarding rolling things. And I invite your attention to this because it is a very powerful question. Supposing I had a wheel rolling without slipping on a surface, and I considered some point on the wheel. And I ask you, as the wheel rolls, what kind of a path does this point make? What kind? Well, some people draw something like this. All kinds of twisty matters. I'm going to show you because it is a very important business. The point on the wheel does this. And that curve is a cycloid about which you should read because it has stirred mathematicians for hundreds of years. And I thank you for your attention.